Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. We have been dealing with the continuous probability distributions in the previous sessions. Now, in this session, we are going to deal with another 2 probability distributions, continuous probability distributions, which is of very special kind. In this session, we are going to deal with gamma distributions definition and moments of gamma distribution, and another distribution called beta distribution we are going to deal. But beta distribution has got 2 varieties. One is called beta distribution of first kind, and then we will be deriving the constants of beta distribution of first kind. Also, we will work out some problems in this distribution to understand the concept further. First, let us start with the definition of gamma distribution. A continuous random variable x is said to follow gamma distribution with parameter lambda greater than 0 if its PDF is given by f of x is equal to e power minus x power lambda minus 1 by gamma lambda. Lambda is given as greater than 0 and we have x is also greater than 0. Okay. So, the x ranges from 0 to infinity. This is the PDF of gamma distribution. We will derive the moment generating function of gamma distribution so as to obtain the constants of gamma distribution. With the usual definition of moment generating function, first of all, let us start with the moment generating function formula mx of t, which is given as expectation of e power tx. This is equal to integral 0 to infinity e power tx into f of x dx. But what is f of x here for gamma distribution? It is integral 0 to infinity e power tx into e power minus x power lambda minus 1 by gamma lambda into dx. Clubbing these 2 exponentials and writing in the format so as to obtain the gamma integration formula. I will take that gamma lambda outside, which is constant because the integration is only with respect to x. Lambda is only the parameter. Okay. So, combine these exponentials e power minus of 1 minus t x power lambda minus 1 dx. This is again a gamma formula wherein in the place of a you have 1 minus t. Okay. And integrating this and substituting, you have 1 by gamma lambda, and this is gamma lambda by 1 minus t whole power lambda. Gamma lambda gets cancelled, you have 1 minus t whole power minus lambda. This is the moment generating function of gamma distribution, 1 minus t whole power minus lambda. Using this, we will obtain the constants. Constants of gamma distribution is nothing but mean and variance of gamma distribution. So, to obtain mean using the MGF, which is nothing but d by dt of mx of t at t is equal to 0. You are going to integrate this with respect to t only. Again I am telling you the lambda is only a parameter, and substitute t is equal to 0, and this is minus lambda 1 minus t whole power minus lambda minus 1 with t is equal to 0 into minus 1 is differentiation of 1 minus t inside. So, t is equal to 0 after substituting, mean is equal to lambda. Then how to obtain the variance? Variance is mu 2. Mu 2 is nothing but mu 2 dash minus mu 1 dash square, where mu 2 dash is 2 time differentiation of mx of t at t is equal to 0. This is 2 time differentiated and then t is substituted as 0, we get lambda into lambda plus 1. Substitute here lambda into lambda plus 1 minus mu 1 dash square, mu 1 dash square. So, lambda square. After cancelling you have only lambda. So, variance is equal to lambda. Hence, we have obtained the mean and variance of a gamma distribution, which are called the constants of gamma distribution. Okay. Now, the gamma distribution is defined for one parameter called lambda. Gamma distribution can also be defined for two parameters. Before that, shall we discuss the additive property of gamma distribution using the MGF of gamma distribution. The sum of independent gamma variates is also a gamma variate. That is more specifically, if I want to tell you x 1 follows gamma with the parameter lambda 1, and if x 2 follows gamma distribution with parameter lambda 2, etc., x n follows gamma distribution with parameter lambda n, all these implies the additive x 1 plus x 2 plus etc. plus x n will follow gamma distribution with parameter lambda 1 plus lambda 2 plus etc. plus lambda n, provided these x 1, x 2 etc. up to x n are independent random variables. Now, how to obtain this using the moment generating function of gamma distribution. X 1 follows gamma distribution with parameter lambda 1 implies m x 1 of t, moment generating function of x 1 gamma variable is 1 minus t whole power minus lambda 1. Similarly, x 2 follows gamma distribution with parameter lambda 2 is m x 2 of t is equal to 1 minus t whole power minus lambda 2, etc. x n follows gamma distribution with lambda n is equal to m x n of t is equal to 1 minus t whole power minus lambda n. Again, the additive property of moment generating function m x 1 plus x 2 plus etc. plus x n of t. This is additive property of MGF, provided x 1, x 2 etc. up to x n are independent, then m x 1 plus x 2 plus etc. plus x n of t is equal to the product of the respective moment generating functions, that is m x 1 of t into m x 2 of t etc. m x n of t. We will substitute the corresponding moment generating functions 1 minus t whole power minus lambda 1, 1 minus t whole power minus lambda 2 etc. 1 minus t whole power minus lambda n, which is nothing but 1 minus t whole power minus of lambda 1 plus lambda 2 plus etc. plus lambda n. In the place of lambda you are having lambda 1 plus lambda 2 plus etc. plus lambda n. This looks like a moment generating function of gamma variable. Okay. Using the uniqueness theorem of moment generating function, we will say x 1 plus x 2 plus etc. up to x n is also a gamma variate with the corresponding parameter. In the place of lambda you are having lambda 1 plus lambda 2 plus etc. plus lambda n. So, this particular function being looking like a moment generating function of a gamma variable, this is also a gamma variate x 1 plus x 2 plus etc. that is what is uniqueness theorem plus x n is also a gamma variate with parameter lambda 1 plus lambda 2 plus etc. plus lambda n. Okay. Hence, we have obtained the additive property of a gamma distribution. As I was discussing earlier, gamma distribution was discussed with one parameter. Gamma distribution can also be defined for two parameters. All these definitions are based on the definition of gamma variable. Okay. Gamma variable following a having a probability function will be called as gamma distribution. Okay. So, how does it look like with two parameters? A continuous random variable x is said to follow gamma distribution with parameters a comma lambda, a lambda both are greater than 0 if its PDF is given by f of x equal to a power lambda e power minus a x, x power lambda minus 1 by gamma lambda, where already given a lambda both are greater than 0 and you have the x limits as 0 to infinity. Okay. This is the gamma distribution with two parameters a and lambda. Based on this, sometimes some of the authors have described this gamma distribution with two parameters as general gamma distribution. Gamma distribution can be done with one parameter, also with two parameters, that is why this definition has been given. Now, let us look at this example. What does the example says? This typical problem we have done with the exponential distribution, wherein we had only one parameter. Now, we shall do this with two parameter, wherein here the random variable is following a gamma distribution. The daily consumption of milk in a city in excess of 20,000 liters is approximately distributed as a gamma variate with parameters a is equal to 1 by 10,000 and lambda is equal to 2. The city has a daily stock of 30,000 liters. What is the probability that the stock is insufficient for a particular day? Now, as discussed in the previous this thing, we will take y as daily consumption of milk. Daily consumption of milk, then x is equal to y minus 20,000 is a gamma variate, whichever is excess of 20,000 gamma variate, and we will write down the PDF of gamma variable x with two parameters, which was discussed in the previous slide. F of x is a power lambda e power minus a x, x power lambda minus 1 by gamma lambda, a power lambda e power minus a x, x power lambda minus 1 by gamma lambda, where a is given to be equal to 1 by 10,000 and lambda is equal to 2. We will substitute all the values. So, f of x, we have to construct this f of x first of all after substituting the a values, 1 by 10,000 whole square e power minus 1 by 10,000 x, x power 2 minus 1 by gamma 2. So, what all these things we will simplify this, 1 by 10,000 square e power minus x by 10,000 into x by gamma 2 is 1 factorial. Okay. So, this is 1 by 10,000 whole square x e power minus x by 10,000. This is the f of x. We have to proceed to finding the probability with this f of x. Now, what is the question? The question is, what is the probability that the stock is insufficient for a particular day? As discussed earlier, the city has a daily stock of 30,000 liters. When the stock is insufficient, when the demand or the consumption is more than 30,000, when the consumption is more than 30,000, then the stock is insufficient. So, the consumption being denoted as y, when the consumption is greater than 30,000, we will have the stock is insufficient. So, required probability, the stock is insufficient, it is asked only for one particular day, therefore, we will have the probability for only one day. Required probability is the consumption greater than stock. This is consumption, right? Consumption is greater than stock. We will have insufficiency. These two will give you insufficiency, right? So, what is y? Y is p of x plus 20,000, which is greater than 30,000. Taking the 20,000 to the other side, p of x is greater than 10,000. Okay. 10,000 means what are the limits? 10,000 to infinity, 1 by 10,000 square x e power minus x by 10,000 into dx. We have to integrate this and obtain the limits. Whole square is taken outside, and using a UDV method or Bernoulli's formula, x e power minus x by, because integration is very important, let me do this, within the limits 10,000 to infinity minus e power minus x by 10,000 by 1 by 10,000 whole square. After substituting the limits, we have the answer as 2 e power minus 1, 2 by e. This is the answer. So, the probability that the stock is insufficient for a particular day is given by 2 e power minus 1 or 2 by e. So, the gamma distribution is discussed. Next, we will discuss the beta distribution. Beta distribution has got two varieties. One is called beta distribution of first kind and another one is called beta distribution of second kind. Because beta function can be defined, can be represented as two formats. Based on the beta variable being represented as two formats, beta distribution also has two varieties. One is beta distribution of first kind and beta distribution of second kind. So, how to write down the PDF of a beta distribution of first kind? A continuous random variable x is said to follow beta distribution of first kind with parameters m comma n. M is greater than 0, n is also greater than 0 if its PDF is given by f of x is equal to 1 by beta of m comma n x power m minus 1 1 minus x whole power n minus 1, where m n already given to be greater than 0 and the limits of x is only from 0 to 1 in this format. Beta distribution of first kind, limits is limited only from 0 to 1, okay, and it is equal to 0 otherwise. We say that if this particular x follows a beta distribution of first kind with parameters m comma n. When this PDF is in this format, we say x follows beta distribution of first kind. First kind is represented as 1, beta 1 of m comma n. Particular case, if you take m is equal to 1 and n is equal to 1, what happens? F of x is equal to 1 by beta of 1 comma 1 x power m is substituted as 1. So, 1 minus 1, 1 minus x whole power 1 minus 1, then it becomes beta of 1 comma 1 because x power 0 and 1 minus x whole power 0 becomes 1. This is equal to 1 because beta of 1 comma 1 is also 0. We have since beta of m comma n, this formula is known gamma m into gamma n by gamma m plus n. So, beta of 1 comma 1 is gamma 1 by gamma 2, which is nothing but 1. So, f of x equals to 1 for 0 less than x less than 1, which is the PDF of uniform distribution, right, because the interval is also 0 to 1 and f of x is 1 by 1 minus 0, uniform distribution. Beta distribution of first kind reduces to uniform distribution in a particular case where m is equal to 1 and n is equal to 1. Next, we shall derive the constants of beta distribution. The constants of beta distribution of first kind is nothing but the mean and variance of beta distribution. Let us derive this mu 1 dash. First of all, we shall have the rth moment mu r dash, rth moment. After obtaining the rth moment, after substituting r is equal to 1 and r is equal to 2, we will get mu 1 dash and mu 2 dash. Using mu 2 dash, we can find out the variance as mu 2, right. So, first of all, we shall find out mu r dash, which is integral 0 to 1 x power r f of x dx, because limits is from 0 to r, integral 0 to 1, 0 to 1 x power r, what is your beta function? 1 by beta of m comma n x power m minus 1, 1 minus x whole power n minus 1 dx. So, integrating this 1 by beta of m comma n, integral 0 to 1 x power m plus r minus 1, 1 minus x whole power n minus 1 dx. Okay. And this is written as this is in the form of beta integral, where in the place of m you are having m plus r. So, this becomes beta of m plus r comma n. And write down the gamma formula. Always beta can be divided only with gamma. Gamma it can be simplified with the gamma function formula. So, gamma m plus r gamma n by gamma m plus r plus n by gamma m by gamma m plus n. What all can be cancelled? This gamma n and gamma n can be cancelled. So, writing it in the simpler format, taking that gamma m plus n above gamma m plus r gamma m plus n by gamma m plus r plus n into gamma m. This is your mu r dash. So, what is mu r dash? Mu r dash is equal to gamma m plus r gamma m plus n by gamma m plus r plus n into gamma m. We have to find out the mean. What is mean from rth moment mu 1 dash? Put r is equal to 1. When you put r is equal to 1, what happens? Gamma m plus 1 gamma m plus n by gamma m plus 1 plus n into gamma m. Okay. So, we know that gamma m plus 1 can be written as m gamma m. Okay. Using this formula, gamma m plus 1 is written as m gamma m into gamma m plus n is written as it is, and this is gamma m plus n plus 1. So, this is gamma m plus n plus 1. So, this can be written as m plus n into gamma m plus n into gamma m. What all can be cancelled? Gamma m cancelled, gamma m plus n cancelled, and you have only m divided by m plus n. This is mean of beta distribution of first kind. Next, we have to find out the variance. Variance is nothing but mu 2. Mu 2 is mu 2 dash minus mu 1 dash square. What is mu 2 dash? Mu 2 dash is substituting r is equal to 2. So, that becomes gamma m plus 2 gamma m plus n by gamma m plus 2 plus n into gamma m. This m plus 2 can be written as m plus 1 into gamma m plus 1. Gamma m plus 1 can be again written as m into gamma m. Okay. Using this, we write as m plus 1 into m into gamma m plus n by, again using the same format, it is first of all m plus n plus 1 into m plus n into gamma m plus n into gamma m, this one. Gamma m gets cancelled, gamma m plus n gets cancelled. So, the remaining is m plus 1 into m by m plus n plus 1 into m plus n. This is mu 2 dash. So, variance is 2 is equal to m plus 1 into m by m plus n plus 1 into m plus n minus m by m plus n. This is already we have found out mu 1 dash square, mu 1 dash. So, m by m plus n whole square. After simplifying, we have mn divided by m plus n whole square into m plus n plus 1. Hence, we have derived the variance of beta distribution of first kind. Hence, we have derived the constants of beta distribution of first kind, that is the mean is m by m plus n and variance is mn by m plus n whole square into m plus n plus 1. Now, in this session we have discussed the definition of gamma distribution with one parameter, and then the definition of gamma distribution with the two parameters, and then we have discussed the moment generating function of gamma distribution, and using moment generating function we have also discussed the additive property of gamma distribution. After studying gamma distribution with an example, we stepped in to discuss the beta distributions. First of all, we have discussed the beta distribution of first kind. Beta distributions first kind's definition was discussed, and then we have derived the constants, that is mean and variance of beta distribution of first kind. Thank you.